The vector field was F equals 2x plus y, 2y plus x. And C is the curve parameterized by R of t equals t squared minus t, comma, t cubed minus t, for t between 0 and 1. Okay, first thing to do is to find a potential function for f. Evidently, it has one. Not all vector fields have one. That's the first thing you should realize. Not all vector fields have potential functions, they are the gradient of. In fact, if you didn't know it, in general, usually they don't. We'll talk about why this has a potential function in a minute, but let's just try to find it. This is supposed to equal the gradient of some function f. What is f is the question. F is going to be a scalar function. You could even call it a scalar field, but it's not a field in the sense of a vector field. It takes on scalar values. It's not a vector. This is supposed to be the gradient of f. So you want this to be the partial of little f with respect to x, and you want that to be the partial of little f with respect to y. You find little f just by integration. Using the fact that that's the partial of little f with respect to x, we could say little f of xy is the integral of that thing with respect to x. Write it as an indefinite integral. Integrate with respect to x. Treat the y as a constant. Don't forget your constant of integration, though. It's an indefinite integral. Then remind yourself when you write the c down that, hey, when I did this calculation, I thought of y as fixed. So this constant could depend on y. And maybe I should call it C1, because if I use the other derivative to solve for f, I'll get another constant of integration that I should probably call C2. So integrate this with respect to y, get y squared plus xy plus a constant that depends on x. And you can make these match up as long as you pick C2 to be x squared and C1 to be y squared. So a little f of xy is x squared plus xy plus y squared. Should I add another constant c to this? You could, it wouldn't hurt, but you don't need to. It's kind of like with regular antiderivatives in Calc 1 and Calc 2. You put the plus c there, especially if you've got an initial condition that needs to be satisfied. But if all you need is one antiderivative, as you do with just the fundamental theorem of calculus, to evaluate integrals, you don't need the c. This is a potential function. It's not the potential function. It's one potential function out of many, out of infinitely many. And it is a function. It's not potentially a function. It is a function. We call it a potential function because it corresponds to potential energy. So that's a potential function for capital F. But remember, typically, most vector fields, if you write down a random vector field here, or a random formula, in all likelihood, it will not have a potential function. It's very special for the vector field to be the gradient of some scalar function. That's very special. Could I have predicted that I'd be successful without actually doing the integrals? And by the way, if you try this method with some vector field that does not have a potential function, you won't get consistency here. You won't be able to line up these constants of integration in a way that'll make sense. That's what will go wrong if you try it for a vector field that does not have a potential function. But is there a way to figure out whether this has got a potential function ahead of time? Yeah, you can use the curl. Call that capital M and that capital N. The scalar curl of F being a two-dimensional vector field, we can think of the curl as a scalar. You can also think of it as a vector. I reminded you of this It's in the reading. For a two-dimensional vector field in the plane, if you compute the regular curl for it, you get a vector pointing straight up or straight down, perpendicular to the plane with the x and y components that are zero. The only non-zero component is the third z component. So effectively, in writing down this formula here, that you do nx minus my, we're looking at that third component. You can call this a scalar curl if you like. In general, the curl is a vector. So looking back up at this formula, nx, the derivative of that with respect to x is 1. My, the derivative of that with respect to y is also 1. So the scalar curl becomes 1 minus 1 is 0. No matter what x and y are. In general, the curl and the divergence depend on x and y, and maybe z with a third component. But here, with this example, it doesn't. And it's a constant, and in fact, that constant is 0. This is for all x and y. I'll write those as points for all x, y in the plane. And we have, a theorem that says you got a vector field whose components are nice and continuous on a simply connected domain, which basically means there's no holes in the domain, at least if it's a domain that's in the plane. Should have read about that. Then f is conservative if and only if the curl is 0. We got an example here where the curl is always 0. So this vector field is conservative. What does that mean? It means it's got a potential function. It's the gradient of some scalar function, little f. Kind of like an antiderivative. Potential functions are kind of like antiderivatives. Not the exact same analogy, but similar. It also means when you do a line integral for it, it's independent of path. You don't need to worry about what the curve itself is, just the starting point and the ending point. And to evaluate the line integral, you don't have to use a parameterization. You can just plug in the points into the potential function. We've done parts A and B, found the potential function, find the curve. Part C, evaluate the integral directly. Part D, use the theorem. So let's get more practice with the line integral itself. Here again is our R of t. I'll rewrite everything down here. So f is 2x plus y, comma 2y plus x. R of t is t squared minus t, comma t cubed minus t. By the way, if you graph this, I mean, you didn't have to graph it. If you graph this parametric curve as t goes between 0 and 1, when t is 0, you're at the origin. You get 0 minus 0 in each case. When t is 1, you're actually back at the origin. This is going to be a closed curve. When t is between 0 and 1, for example, at 0.5, 0.5 squared minus 0.5 is negative. X is negative. And y is also negative, it looks like. Actually, I better use technology just to make sure of this here. So R of t is t squared minus t, comma t cubed minus t. If you do a parametric plot of this, there's what it looks like. Make the scale bigger. Okay. You go down and come back. Is it counterclockwise or clockwise here? That's hard to tell just looking at the formulas. Let's use the technology again. If we plotted this for t values just barely bigger than 0, you can see we're on the upper half. So this is counterclockwise. It's an oriented curve. The arrows are going counterclockwise around. But you're coming back to where you start. We already know this is a conservative vector field. It's independent of path. A and B are the same point. I know I've got to get 0 for the answer. The integral has to be 0. Let's confirm that, as you should have done the homework. R prime is 2t minus 1, 3t squared minus 1. F of R of t, I need to plug in this x and this y into here. So I get 2 times t squared minus t plus t cubed minus t. That thing gets multiplied by 2. This thing is just added. Comma 2y, 2 times t cubed minus t plus x plus t squared minus t. Simplify. T cubed plus 2t squared minus 3t, it looks like. And then 2t cubed plus t squared, also minus 3t. Does that look good? What we end up having to integrate is the dot product of these things. Which is, it was kind of a pain. For the sake of doing more examples, let's have Mathematica do it. If I'm going to do this efficiently in Mathematica, it's also nice to plug in the formula for capital F. And again, not that you have to do this, but as a default, I like, with my vector fields, I like having curly braces around the x and the y. Because again, that allows me to plug in points into F if they are represented with curly braces. Just gives me a little more flexibility. So F, well, for example, like right here, F of R of t. R of t is a vector, but in Mathematica, it's a list. Because I have this as a list in defining capital F, I can do this. I can plug R of t as is into capital F. Dot is with a period. There it is. Simplify. That's the function we have to integrate. I think I can just do expand, actually. So you should have integrated this and you should have gotten 0. Integrating by hand is not too bad, but let's just do it like this. 0. You had to. Again, this vector field has a little f, has a potential function. It is a gradient of the function little f. It's conservative. Therefore, line integrals are independent of path. It only depends on the starting point and the ending point. The line integral around a closed curve like this is going to be 0. Because the starting point and the ending point are the same. Could I use little f here? What was little f? It was x squared plus x times y plus y squared. Sure, but in kind of a trivial way. You're really doing little f of 0, 0 minus little f of 0, 0. That's a calculation you should have done by hand for part D. It's got to be 0. You're ending at the same point. It doesn't mean little f of 0, 0 in general is 0, though it is here. But you are starting and ending at the same point, so you're subtracting something from itself. A equals B. Let's continue with this example. Make this bigger. Let's relate it to Green's theorem now. As well as understanding exactly what's going on with this thing. So let's plot the vector field. Vector plot does that. If I use curly braces to define the vector field, I need to use curly braces here as well. There's the vector field. Looks like the origin is some sort of source, if this were representing a fluid flow. The divergence should be non-zero. Let's think about what the divergence of this would be. Look up here. The divergence is the derivative of m with respect to x plus the derivative of n with respect to y. 2 plus 2, 4. Yeah, the divergence is the constant function 4. That's consistent with the origin being a source. But that divergence is for everywhere in the entire plane. Over any small region, no matter where you are, more water, so to speak, is flowing out than is flowing in over any small region. It's hard to visualize and think about just looking at this picture, but it's true. Here's sort of an intuitive way to think of it. If you draw a small circle near, say, this point here, the vectors do get longer the further you get from the origin. So what happens is the vectors are longer on the side of the circle that's further away from the origin than they are on the side of the circle that's closer to the origin. The velocity of the molecules is faster speed, I should say, when you're further from the origin than when you're closer. So they're going out faster than they're going in. That might seem like that might be impossible to happen physically speaking, right? How can more be going out than going in? And maybe that's true. But if you do imagine it to be a fluid flow, it's got positive divergence. You also want to put the parametric curve in here. Let me go from negative 1.5 to positive 1.5 instead. And let's put the parametric curve in there with parametric plot. R of t goes from 0 to 1. Make it easy to see. Let's do green. Oh, still kind of small. Okay, go closer. There we go. Okay, a little easier to see. Oh, too thick. Okay. What are you really doing when you do the line integral? You're integrating the vector field along the curve, which means you need to think about dot products of the vector field with the unit tangent vectors. Or if you prefer, this dot product here of f at r of t with a velocity vector r prime of t. Let me add graphics, thick red arrowheads, 0.1. What am I going to add here? I'm going to add velocity vector. And I'm also going to add the vector field. If I add the true velocity vector, it's probably too long. I may need to scale it down. Let me try scaling it down by a factor of 2. This is going to be the velocity vector along the curve as time goes by. I guess we don't need to worry about putting the vector field in there because you can kind of see it. As t is between 0 and 0.5, notice that the arrow is pointing, generally speaking, in the same direction as the velocity of the vector field, which is in the background. Generally, they're parallel and they're pointing in the same direction, meaning the dot products are close to being maximized because the angle between the vectors is close to 0. The dot product would be the length of the velocity vector with the length of the vector in the vector field. However, once you get past time 0.5, now the vectors are pointing in the opposite direction. R prime, that's the red vector, is pointing in the opposite direction approximately with capital F, vectors in the vector field, leading to dot products that are negative. And because of that, it should be somewhat intuitive that they would kind of cancel out. The positive contributions of the dot products to the integral value should cancel out with the negative contributions. Another way to think about that is if you actually plotted this function, that is the dot product right there, as an ordinary graph. Probably it's positive for small values of t and negative for large values of t. Yeah. And it was the integral of this function ultimately that was 0. These two areas cancel out. But the fact that we're positive over here corresponds to the red arrow being in the same general direction as the vector field when t is small. And then you turn it around and they're pointing in generally opposite directions when t is large. And they are canceling out. The circulation around the curve, let's see here. which is defined to be the line integral of f around the curve, is 0. Should have read about this to emphasize this is a closed curve coming back to where you started. Sometimes put a little circle there. I also even like to put an arrow on that circle, if I think about it at least, to indicate the direction that the curve goes, in this case, counterclockwise. Yes, this is not a circle, whereas that is a circle. Don't worry about it. It's not a big deal. The key thing with the circle here is that it's a closed curve. It comes back to where it starts. The book doesn't put an arrow on it. If you do put an arrow like I drew it, that's emphasizing that you travel around the curve counterclockwise. I could put a clockwise arrow if I was going clockwise. I think that's worthwhile to keep track of. Though I don't know a way to get it to show up on my typesetting when I write tests. So if you look at the old final exam from a few weeks ago when you were studying for exam 3, one of my old final exams, I just put plain old circles on these things. This is called the circulation of F around C. It's sort of measuring how much F flows with the vector field, you might say, is generally speaking in the same direction. Taking into account angles, because you've got dot products, and taking into account lengths of vectors in ways that the animation didn't really show very much. What does Green's theorem say? Which I guess I should write in green. Green's theorem. It is a theorem, so to fully write it out, I should state it carefully. Basically, the assumptions amount to you've got a vector field that's nice, that has continuous components that are also differentiable, and I believe those derivatives have to be continuous, on some domain in the plane, containing a closed curve, oriented counterclockwise. So the arrow points counterclockwise. Green's theorem says that one way to integrate the vector field over the closed curve is to do a double integral of all things. A double integral of the scalar curl over the domain that's inside C. It's pretty amazing. Who would ever guess such a thing would be true? Well, evidently Green did. He guessed it and then he used it. Probably didn't prove it, I imagine. It's more of a scientist for one thing, and also just even mathematicians from 200 years ago didn't really prove things rigorously. Now maybe from more like 250 years ago. They gave intuitive heuristic arguments instead of rigorous proofs. And if F is conservative on D, that implies the scalar curl is 0 on D, which implies the double integral of the scalar curl is 0, which implies the line integral of F around C is 0. i.e., the circulation is 0. In fact, if F is conservative on the entire plane, then it's conservative on any domain D, and the scalar curl is 0 on any domain D, and the circulation around any closed curve is 0. It doesn't mean the circulation around a piece of a closed curve is 0, or the circulation along a piece of a closed curve. But when you come back to where you start, you got to get 0. And that's because another way to see that is because the line integral is independent of path. If you end where you start, you got to get 0 by the fundamental theorem from the previous section. So it's two ways to see that the answer has got to be 0. With the fundamental theorem in the previous section, using the potential function little f, or using Green's theorem here in this new section. But Green's theorem applies to situations where this vector field is not conservative, where there is no potential function, where the scalar curl is not zero. Green's theorem still applies.